So the next presentation is given by Geneviève Dusson, who is a researcher at CNRS in applied mathematics at the Université Marie-Louis Pasteur in Besançon. And so she will speak today about metric-based nonlinear model order reduction with application to quantum chemistry.
Thank you very much, Yvon. Thanks a lot for the invitation to this super interesting workshop. So in this presentation, I would like to talk about my attempts at developing nonlinear reduced order models, which are metric-based. So the main idea will be that we go from the linear world to the nonlinear world by going from vector spaces to metric spaces, and we replace linear combinations by barycenters. And I will show how this applies to quantum chemistry and in particular electronic structure calculations. Okay, so my framework is really standard. So I have a parameterized PDE and my parameter will be denoted by R throughout the presentation. And as many of you here, I want to efficiently approximate the manifold of solutions when this parameter vary. And so in my case, so I'm interested in modeling systems at the atomic scale. So basically a molecular system is usually modeled as a collection of nuclei and electrons. So the nuclei, due to the fact that their mass is way higher than the mass of the electrons, they are modeled as classical particles. So they are characterized by positions. So R in R3M, so when I have M nuclei, so this will be my parameters. And then the system has N electrons, which are described by a wave function, psi R. Which is a very high-dimensional object. So in general, this is a function from R3N to C. And the physical meaning of the wave function is that the modulus square of the wave function is the probability density of finding the first electron in the first position up to the nth electron in the nth position. And so a very nice feature of the wave function is that it can be used to recover many physical properties, such as the energy, the forces, polarizability, or even more complicated properties. Okay, and so in this field, somehow one of the basic questions is to characterize the ground state of the system. So the ground state is the state with lowest energy. Usually it characterizes the most stable state of the molecule. And so mathematically speaking, it's an energy minimization problem. So we minimize the expectation value of the Hamiltonian, where the Hamiltonian is an operator which is parameterized by the position of the nuclei through the Coulomb interaction between the nuclei and the electrons. So this is this thing here. Okay, and if we write on the, it can be recast as an eigenvalue problem, which is exactly the Schrödinger equation, which is now 100 years old. And so in practice, this equation is way too expensive to be solved exactly. And so the physicists and the chemists have been working on developing many approximations over the past 60 years, such as Hartree-Fock, post-Hartree-Fock, or density functional theory. So in this presentation, I will focus on the Schrödinger equation, but in a toy setting, so my particles will be in 1D, and in the first model I will show I will even have only a single electron. But the reduced model I developed, the idea was that we still want to keep in mind that in the end we want to deal with high-dimensional problem, and so we will see how this comes into play in the reduced models. Okay, and so just to give a little idea of how this object looks like. So in fact, so as said, the object of interest is the wave function, which is this very high dimensional object. But in practice, one can reconstruct exactly the energy with 3 low dimensional objects computed from the wave function. So namely, the first one, which is the electronic density. So the electronic density is defined as the modulus square of the wave function, where we integrate out all the variables except the first one. So just as an example, so if I take 2 nuclei in a 1D setting and I take them apart, this is how the electronic density looks like. So we see that the electronic density is highest near the nuclei. So this is where the probability of finding the electron is the highest. And to reconstruct the energy, we also need the two-body density, which is the modulus square of the wave function integrated out over all variables except 2. So here this gives such a picture, and so here we have on top of the probability of the electron the information about the correlations between the electrons. So for example, on the right here, what we see is that if we have one electron sitting at one position, then necessarily the other electron will be at the other position. So here we see that having the 2 electrons at the same position, we have probability 0. Okay, and the third object that we need to reconstruct the energy is the density matrix, which is defined like this. So this is psi r star psi r, where we keep an x here and a y here, and then we integrate out all other variables. And so here we have something like this. And here, the link between the density matrix and the electronic density is that the diagonal here is the electronic density. And one thing I forgot to mention, so here, due to the definition of the two-body density, if we integrate out on any of the coordinates, we get back the electronic density. Okay, and so. Since somehow these objects are kind of enough to reconstruct all what we need to compute electronic properties, I will try to build reduced models for these objects. And so in my talk, I would like to present 3 different examples. So the first one will be inspired by learning the electronic density. So in fact, it's on a toy problem where we have only 1 electron, so somehow we can directly look at the wave function. And then I will also try to, I will show how we approximate the two-body density from the knowledge of the electronic density. And finally, I will discuss how to deal with the density matrix. Okay, and so let me start by explaining how we go from this linear setting to the nonlinear setting. So I know all of you are familiar with that, but so just to highlight the difference later, I just want to set up the scene on a greedy algorithm, which is for a projection-based reduced order model. So in that case, one of the main point is that both in the offline phase and on the online phase, the solutions are approximated as linear combinations of the chosen solutions. And so this works for many problems where the linear Kolmogorov n-width decays fast. So this is, for example, the case for nice elliptic equations where the Kolmogorov n-width decays exponentially. but somehow for our problem, this is not the case. So we are closer to what happens for transport equation, where we know that the Kolmogorov n width decays like n to the minus 1/2. So in fact, what we showed is that so in this for this toy problem, so which corresponds to the Schrödinger equation in 1D with just one electron and changing the Coulomb potential by Dirac delta potentials. So here, this is how the solutions look like when we only have a single nucleus. So what we see is that if we just translate, if we change the position of the nucleus, the solution is just translated. And so what we showed for this problem is that the linear Kolmogorov n width decays as n to the minus 3/2, so pretty slowly. And so we needed somehow to introduce some nonlinearity. So we have seen over the past talks many different possibilities. So I will, let's say, add one to the list, which is to replace these linear combinations by barycenters. So the idea is to place ourselves in a metric space, M, and then in this metric space, we consider a distance d. And then we define the barycenters between n snapshots as the argmin of this cost function here, so the sum of lambda k, the distance between u and psi rk squared. And what is nice about this is it can really be seen as a generalization of a linear combination, because if you replace this distance d, you take the Euclidean norm, what happens is that the solution to this problem is really just a linear combination of these psi rk. And so using this definition, we introduced another notion of Kolmogorov n width, which is really linked to this metric approach. So we, given a metric space M, we define it as the infimum over n chosen snapshots, and then we look at the supremum and of the distance between the chosen solution, so psi r, and the best barycenter we can get using this distance. Okay, and so so now if we think about a strategy to put that in practice, so what we can say is that we do a greedy algorithm in the same way as before, except that instead of linear combination, we consider these barycenters. And in the online phase, for the wave function, so in the case of the Schrödinger equation, since we have a minimization problem to solve, what we did was to just minimize the energy of a set of barycenters generated by the selected snapshots. Okay, and so then somehow the main question, the natural question, is how do we find a metric that is adapted to the problem at stake, and so adapted to the solutions to our equation. So one natural criterion for this is that the decay of the Kolmogorov n width should be as fast as possible. But then, as I will show later, there are also physical constraints coming from the solutions to the problem, which needs to be satisfied and which may be hindered by a metric, chosen metric. And then, of course, a very important question is the computational cost of the barycenters, which may not be easy to do in general, because it requires to solve this minimization problem. Okay, and so this is where we somehow try to use optimal transport. And so there were actually previous works mentioning possibilities like this. And so our main motivation into this was that at least somehow it deals with the translations. So if we have two solutions like this, then the barycenters between the two solutions will be just a translation from one to the next. And so this sounded well adapted to our problem. Okay, so the Wasserstein distance. So here we used the two Wasserstein distance, which goes back to Monge and is defined here in this Quantorovich formulation as the infimum over all transport plant with some marginal constraints of some transport cost. And so this defines a distance, and using this distance, one can compute barycenters by solving the, so as a so-called Fréchet mean, so solving this optimization problem. And so in that case, if I take one solution in blue and another one in red, the barycenter between the two is the green thing here, and so it sounded pretty well adapted to the solutions to our problem. So somehow the mass of the solution seems to be located close to the nuclei as expected. Okay, and theoretically, so due to this translation property, we very easily obtain that the nonlinear Kolmogorov n-width in this setting is 0 when we have more than one solution. And then for two nuclei, this is not that easy, but we managed to prove that the Kolmogorov n-width decays faster than n to the minus 5/2. So before we had n to the minus 3/2, so this is not perfect. And in fact, in practice, we observed something more like exponential, but we weren't able to prove that the nonlinear Kolmogorov n-width decays that fast. And we were still pretty happy to show that there was some kind of improvement in the Kolmogorov n-width. Okay, but now there are a few limitations. So in general, computing Wasserstein barycenters is very expensive, and so this is a computational bottleneck. And also one problem is that due to the use of specific algorithms with some kind of regularization to compute the barycenters, they in general do not preserve the structure of the solution. And so if I go back to this example, so what we see here is that, so the solutions that we have are actually a mixture of slider functions, so really sharp functions. And what we see is that the barycenter smoothes out a little bit the solution, and if you go to higher dimension and you need to perform very big simulation, you will be forced to use like a pretty large regularization parameter, which will completely destroy the structure of the solution. And this will be a problem. And then I will show later that there are also problems that the marginals are not preserved. And also, I forgot to mention that, but this distance, this Wasserstein distance, is limited to probability measures. Okay, and so about the cost of the barycenter, so the thing is that the Wasserstein distance is in general expensive to compute, except in few particular cases. And so one particular case is the optimal transport between Gaussian measures. And so in that case, we have an explicit formula of the Wasserstein distance, which is just the Euclidean distance between the centers and the Bose-Wasserstein metric on the covariance matrices. And we also have that the barycenter between Gaussian measures is also a Gaussian, where the formula for the center is explicit and the formula for the covariance matrix is not fully explicit, but it's just a solution to some nonlinear equation which can be easily solved. And so if now we look at the barycenter between those three, we will have another Gaussian somewhere in the middle. And so this is actually very convenient, because what we try to use afterwards is a so-called mixture distance. And so the idea is that we write the density that we are looking at as a mixture of some functions. So typically, so they have to be of some class, so either Gaussians or slider functions. And then we used a mixture distance defined originally by Julie Delon and Agnès de Zolneux, where we solve a discrete optimization problem where somehow the distance, the cost between the points is replaced by the Wasserstein distance between the atoms, so these Gaussian functions or these slider functions. And so what is very nice about this formulation is that it's completely independent of the spatial dimension. So somehow in our case, if we go to 3D, this won't hurt us. The only thing that matters is the number of functions that are in the mixtures, and this is what plays the role of the complexity in this case. And what also happens is that there is a nice formula for the barycenters. So the barycenter will be basically a convex combination of individual barycenters between these atom functions, so these Gaussians or Setter functions. And so in the case where the Wasserstein distance between the atoms can be computed explicitly, then this distance can be computed efficiently. And so coming back to our parameterized solutions, so what we managed to prove in that case is that for this mixture distance, actually we have that the nonlinear Kolmogorov end width is 0 for two symmetric atoms. So we have, so in fact here, so in green we have the barycenter, and it's actually exactly the solution between the two solutions. Okay, and so we performed a greedy algorithm to select specific snapshots. So here we use a case where we have two nuclei with different charges. And so what we see, interestingly, is that so here in red we have the error when we select with respect to the Wasserstein distance. And in purple here we have the error when we select with respect to this modified mixture Wasserstein distance. And so the two plots are both measured in Wasserstein distance. And so what we see is that very nicely we gain more than 1 order of magnitude in the error when we select with respect to the mixture Wasserstein distance. So somehow adapting the metric to the problem at stake improves a lot the situation. Okay, and so, sorry, I just... Okay, and so in the online phase, so we minimize the energy over the set of possible barycenters, and so what we also nicely see is a very important decay of the error. And we see that we gain about 3 orders of magnitude in the energy with a selection of less than 10 basis functions. So the decay is really sharp. Okay, and so then having this at our hands, so we try to develop reduced order models for the pair density. So somehow we have the information of the density. So one thing I should mention is that in practice it's often easier to have access to a good approximation of the density here compared to having a good approximation of the pair density. So our idea here was to say we have a database of densities and corresponding pair densities, and then we want to construct approximations of the pair densities knowing the density. And so, as I said at the beginning of my talk, there is a link between these one-body and two-body densities, which is that the marginal of the two-body density is the one-body density. So there is some marginal constraint. And so what we thought is that we say we will approximate this pair density as a Wasserstein barycenter or modified Wasserstein barycenter of selected pair densities. But then we would also like that the corresponding density match, so that the corresponding density is also a Wasserstein barycenter between the corresponding densities. And the problem is that this is not true in general. So it took us a while to understand this, and it was quite a surprise, but so it's not true. The Wasserstein barycenters don't preserve marginals. And so we found two. So what we developed was a marginal constraint, a modified Wasserstein barycenter, and so the idea, so there were somehow two natural formulations for this. One was to say we have a known barycenter in Wasserstein 2, and we minimize the Wasserstein 2 distance between this barycenter and some two-body density that will satisfy the marginal. And the other possibility that is natural is to say I minimize, so I look at the Frischer-Mean formulation, so I minimize this cost function and I constrain the marginal. And so what happens is that in practice, it turned out to be easier to look at the first formulation for the reason I will show you. So in a simplified setting of a single Gaussian measure, so in that case, so let's say we have the space that separates in 2 dimensions. So we consider a 2D Gaussian. So we have a center which can be decomposed as mu x, mu y, and the covariance matrix can be also block decomposed. And so what is very nice about this is that the marginals can be explicitly written from this block decomposition. So the marginal in X will just be a Gaussian centered at mu X with covariance Sx, and the same with the Y for the marginal Y. And so somehow our problem was to minimize the Wasserstein 2 distance between some reference solution and the one that we want, where this tau here satisfied the marginal constraint. And so what happens is that we have a partial answer. So already, since we have these equations, we know that the center has to be mu x, mu y, and that the diagonal blocks of the covariance matrix are given by the prescribed marginals. And so the only freedom that we have is on this off-diagonal block here. And in fact, what is pretty nice is that if we look at this minimization problem, there is a unique minimizer, and this unique minimizer has even a formula, which is here, so it's a bit complicated because it involves this Hoffel formula of the geometric mean of covariance matrices, but we can easily compute it. This is no problem. So at the end, what we have is that the solution for single Gaussian is a Gaussian with the center given by the prescribed marginals and the covariance matrix given by this so the diagonal blocks given by the marginal and the off-diagonal block given by the formula I just showed before. Okay, and so this was for single Gaussians, and then we extended this to Gaussian mixtures. And so the idea, so I spare the details, but the idea is to write somehow a similar optimization problem using the Wasserstein mixture distance, and then we simplify this problem by choosing specific Gaussians based on this, actually. And then at the end of the day, what happens is that to get marginal constraint Wasserstein barycenter, we post-process the simple mixture Wasserstein barycenter, and we obtain the solution. Okay, and so when is this in fact useful in practice? So it's useful at least when you have rotations of the distribution. So this is a first example with just simple Gaussian. So here the exact distribution that I want to fit is a Gaussian that is rotating. And so if I compute a Wasserstein barycenter between the first one and the last one, what happens is that I completely lose the structure. So I have a very large difference, which we can see even more on the middle here. And now if we use a marginal constraint Wasserstein barycenter between the two same Gaussians, what we see is that we recover something way closer than the exact barycenter and the exact solution. And of course, we have used more information, but at least for our problem, this is some information that normally we can have. Okay, and I'll give a second example on the Fokker-Planck equation, which is nice because if the solutions at the initial time are Gaussian, they remain Gaussian mixtures. And so here, this is the evolution of the solution. And so on the second line, I have the the true Wasserstein barycenter between the left solution and the right solution, and here are the marginal constraint barycenters. And so here as well, we see an improvement over the standard Wasserstein barycenter. Okay, and we also did some tests on the greedy algorithm to see how things were behaving for our problem. And so here we tested this Wasserstein barycenter, the classical Wasserstein barycenter, against the marginal preserving barycenter. And here we see that we gain about 1 order of magnitude in the error by imposing this marginal preservation. So once again, of course, we use more information in the red curve here than in the blue curve, but we hope that is an information that we can have in practice. Okay, so then somehow I'll move to the approximation of the density matrices, and so which look like this. So basically, we wanted to do the same. So we have a database of density matrices coming from a costly model, and we have the corresponding one-body densities, and we want to construct approximations using the density matrices. Okay, but here somehow a main issue that we have is that the density matrix are not probability measures, so we cannot use the Wasserstein metric directly, and so we have to find a way around. And the thing is that density matrices have some structure. They are self-adjoint operators, they are positive, and they are of trace 1. And so in fact, there is a correspondence between what people call commutative mathematics versus non-commutative mathematics or quantum mathematics, where so basically the analog of probability measures are density matrices. And then there is also a full correspondence between many objects. So for example, the integrals can be replaced by traces. The positive measures are mapped to positive operators. And so in that way, there is really a correspondence between classical probability measures and these density matrices. And so then we wanted to use somehow a quantum optimal transport distance for our problem instead of the classical Wasserstein distance. And so what happens is that in this field, so somehow in the classical optimal transport world, we have a good understanding of when the Kontorovich formulation, the Monge formulation, and the Benhamou-Brenier formulations are equivalent. But in the quantum case, this is not yet the case. So at the moment, I would say many people have proposed many different distances, which sometimes are not even true distances. And so in our case, we focus on the quantum analog of the Benhamou-Brenier formulation of optimal transport for the reason that we were sure that this was leading to a true distance. And so if you are not familiar with this, so the Wasserstein distance in the classical setting using the dynamical formulation is defined as the infimum over curves of densities and speeds, vt, and velocities, of this quantity here, so some kind of kinetic energy with a constraint looking as a continuity equation. And so somehow to go to the quantum world, we need an adaptation of this equation, and so we need to define a few things. We need to redefine the scalar product. Actually, we also need to define somehow the product here, and we more crucially need to define an analog of the divergence operator. Okay, and so what we use is the Carlin-Mass Riemann distance defined in this paper in 2020, which is really the extension of this dynamical formulation of optimal transport. And so the way the divergence is defined is through the commutators of some derivation operators Lj. So somehow we need first to choose some operators Lj, and then the divergence of a vector of matrices B will be defined as the sum of a j of this Lj Bj minus Bj Lj. And then using this, one can define the distance, which is very similarly as in the Benhamou-Breny formulation as the minimum over curves of density matrices and velocities, which are now matrices of the integral of the trace. So this is somehow the equivalent of the energy. And then we have some kind of similar continuity equation to satisfy. Okay, and so with Etienne Obermeyer, I think I have this on the sorry. So with Etienne Obermeyer and Virginie, we worked on numerically computing this distance. So based on time discretization and an SQP method. And since the algorithm was not converging too well, so we had to add a few tricks, including some Barry method and some penalization to obtain some convergence of the method, the algorithm, and to be able to compute the distance. Okay, and so what is nice about this distance is that if we manage to compute the distance, since we have computed the full curves of rho t, so the full curves of density matrices, actually we have the whole geodesic already. So this is pretty nice to see how the barycenters look like in the case where we have only two density matrices. And so this is how this looks like. So in this line here, I have the density matrices for a system with 3 nuclei and 3 electrons. So these are really the solution to the Schrödinger equation with 1D particles. And so this is how this looks. And on the first plot, I compute the quantum optimal transport distance between the leftmost picture and the rightmost picture. And so what we see is that the geodesic for this quantum optimal transport distance match very well with the chemistry curves of density matrices. And so if we look at now the diagonal, which is the density, the electronic density, we see that still, I mean, the densities do not completely match. So we have something that looks similar, but we clearly see a large error. So we have to see how, I mean, if this can be avoided or if it's somehow really hard constraint that is in the formulation of the distance. And in fact, to obtain this picture, we tried many different distances. So in fact, as I said, the quantum optimal transport distance is defined through these derivation operators that appear in the divergence operator. And so we actually tested a 2-parameter set of derivations. So the first one here, I forgot to mention, but we discretize the density matrices in Fourier. So this first operator is like some kind of derivation with some given order in Fourier space, and this L2 operator corresponds to the multiplication with some function. And we also chose them because they satisfy a condition which guarantees that we have a distance. And so we looked at somehow the different errors when we varied these parameters, so when we vary the metric itself. And so, so here, I mean, these are really preliminary tests, so we don't really have a good understanding of why a specific distance would work or not. But what we see is that if we have so this is the heat map for the 3-electron case that I showed. So we have a lowest error, which is somewhere here. And we see that actually for a 2-electron case, the best derivation is not the same, and so we have to still to understand how we can optimize the metric for dealing with a larger system, or how to adapt this metric to a specific number of electrons. Okay, and to finish, so I presented different flavors of nonlinear reduced order models based on optimal transport, and so I wanted to show that if we choose well the metric, then we get more accurate results for the approximation of the solutions, and so in particular constraining the marginals really helps, using mixture distance also help, and in the case of the density matrix, this quantum optimal transport distance seems pretty well adapted to our case. And so these are really encouraging results toward having reduced order models for electronic structure applications. And so now somehow we need to scale these results to a high dimension, and in the meantime, there are still a few problems that we need to solve, but we are pretty optimistic that it can lead to interesting results. Okay, and with that, I thank you very much.
Thank you.